Good morning. This is Michael Dong speaking on video number 16 on HPLC detector, focusing on UV detectors. We welcome LCGC International as a channel collaboration in this video. Here is my agenda. First, HPLC detector, overview and listing of all the HPLC detectors. Second, UV detector, UV vis and photodiode detectors, glossary, fundamentals, operating principle, case study, flow cells, CDS data display, and trends. This slide shows HPLC detectors, the scope. An HPLC detector measures the concentration or the mass of the eluting analyte from the column to monitor one of the inherent physical-chemical properties, such as UV absorbance and other properties. The UV detector is most ubiquitous as a UV vis or variable wavelength absorbance detector or photodiode detectors. My aspects are discussed in a later episode. The reason why UV detection is dominant is for two strong reasons. First of all, it's extremely precise and also very selective and sensitive. Second, most pharmaceuticals are chromophoric, and the assay for potency and impurity in the quality control of drug is one of the most important applications in HPLC. Here's a listing of all the HPLC detector, and as you see, that is a pretty big list from UV detector, diode detector, all the way to MMR and mass spectrometry. And we will actually discuss the one highlighted in red. The table actually summarizes the analytes of each detector type, the property or attribute, and also their sensitivity. Here's a glossary of key terms, and it would talk about some of the highlighted one. We mentioned UV detector, variable wavelength photodiode detector. A monochromator is a system in the detector that allows the selection of a particular wavelength. Source is typically a low-pressure deuterium lamp. A flow cell is a device, flow-through device in the detector with two quartz window or lenses. The absorbance is the negative log of transmittance, or the ratio of the final and the initial intensity of light as seen by the detector. The unit are AU or milli-AU. Beer's law is the most important equation, which says that the absorbance is equal to the product of molar absorptivity, the path length of the flow cell, and the concentration of the separated analytes. A chromophore is part of the compound that absorbs UV or visible light. Noise stands for baseline noise, typically measured as peak-to-peak or root mean square noise. Measure the fluctuation of light intensity as seen by the detector. Here, this table summarizes the advantages and limitations of UV detector. And once again, we will only look at some of the highlighted attributes. First of all, it's medium to high sensitivity detection, very selective detection for chromophoric compound. So most of the time, we would select a wavelength, which is the lambda max of the highest absorbance of the active pharmaceutical ingredient API. In this way, we can measure the API plus all the related substances, because in most cases the chromophore are not broken with degradation products. We mentioned high precision, so routinely 0.2% RSD is easily achievable in the UV detector. Another biggest advantage of HPLC detector is the very large order of magnitude linearity or linear dynamic range, allowing a single point calibration for most assays. So this is a huge advantage versus other detectors that require multiple leveled calibration. There are indeed some limitations. First of all, analyte must have a chromophoric activity. Without that, it would not be compatible. And also the mobile phases must be transparent to the UV to have acceptable linearity and sensitivity. Just briefly on the desirable characteristic of modern UV detector, right? So most important is low noise. I'd like to mention the noise benchmark is plus or minus 1 times 10 to the minus fifth. So this noise is very low, allowing a 5 order of magnitudes of linearity in most cases. And the other attribute that I want to highlight is the low dispersion or band broadening of the flow cell, right? So typically flow cells are pretty small. In HPLC, we're talking about 8 to 10 microliter. In UHPLC, we're talking about a flow cell which is smaller than 1 microliter. However, because the Beer's law is proportional to the path length, it's really important to have a small flow cell but have a path length of at least 1 centimeter for noise or sensitivity considerations. Here is a schematic of the optical bench of a UV visible detector or variable wavelength detector versus a direct detector, right? So the first one is a variable wavelength detector where you have a deuterium lamp, and this part of uh, the optical bench is called the monochromator, where a rotating mirror uh, with lines called the grating, which would disperse the light into different specific wavelengths. And by turning the mirror, the grating, one can select a specific wavelength. Typically, the spectral bandwidth is about 5 nanometers, so you don't really select a single wavelength. And here's the flow cell. And at the end is a photodiode, which is a large photodiode uh, emitting electrons from light intensity. Now, the difference of the photodiode detector optical bench is the fact that instead of the flow cell after the monochromator, you place the flow cell before the monochromator, and all the wavelengths are simultaneously uh, impinged on a diode array, right, which typically consists of 512 to 1024 pixels. This slide is very important, describing the UV detector characteristic. Once again, we show you the Beer's law, which is the absorbance, the negative log of transmittance, equal to molar absorptivity times the path length B and concentration of the analyte C. Here is a schematic of a flow cell showing you a device typically made from stainless steel with the hole in the middle. The flow cell typical ID would be somewhere around 1 millimeter or so, with 2 lenses, focusing lenses, or silica quartz window at both ends, and then connected by the inlet and outlet of the flow cell. Here is the noise and measured by the peak-to-peak noise. And here's the response graph of the response in terms of absorbance versus concentration of a particular analyte. Know that the linearity is measured by the linear portion of the response curve, typically 5 orders of magnitude, and eventually above 2 absorbance unit, signified by the loss of signal. This, at 2, there's only about um, less than 1% of the light getting to the detector. So eventually, the UV detector would get saturated. In this slide, we demonstrate the design of Waters Acuity PDA. This is developed in 2004 with the debut of the Waters UPLC, the first UHPLC commercial system. And the way they get around with making a very small flow cell and having a large path length is instead of using a regular flow cell design, which is a drill hole in a stainless steel block, uh, the actual flow cell is made from a Teflon AF with very high refractive index. The reason why they do that is that they can use a very small diameter flow cell path with total internal reflectance to make sure that there's no reduction of light when the small beam is passing through the flow cell. So with that, they can achieve noise which is quite comparable to a larger flow cell. This is the CDS of chromatography data system display from Empower, which is the Waters primary CDS. Shown here is a contour map where the spectral data from the photodiary device, which capture all the UV spectrum entirely, and one can move the cursor of the wavelength selection to give you different chromatogram at a specific monitoring wavelength by moving it around. And also the UV spectrum is automatically annotated with the lambda max, and you can see the UV spectrum also by positioning your cursor in the software. This schematic shows a case study of the optical design of a modern DAD from the Agilent 1290 Infinity 2 DAD. And the destination of the devices is shown here. Number one is a deuterium lamp. You have a lamp mirror. The flow cell is distinctly different from that of the Waters design, where they use a cartridge design, which is easily replaceable. And the inside, instead of using a Teflon material, a Teflon tube, there's a capillary made from a fused silica, which are coated for total internal reflectance. So it's quite different. And you have different folding mirror. And also, they also have a programmable slit, which allow the user to program different slit width, and also a holographic grating. And finally, a diode array. Most of the material shown in this video came from this white paper published in 2019. It's called Ultraviolet Detector Principle, Perspective, and Practices in LCGC magazine. This final slide summarizes the UV detector trends. Basically, the most important one are low noise and low dispersion, high linearity range, and also easy operation. Once again, I want to emphasize the benchmark for low noise is plus or minus 1 times 10 to the minus 5th AU for PDA. Improved lifetime of deuterium source is important. Deuterium source can actually survive more than 2,000 hours. Linear dynamic range from the LOQ or limit of detection or quantification to saturation, typically saturate around 2 absorbance unit. A low dispersion because of the small volume flow cell specifically designed for UHPLC. And easy maintenance and built-in diagnostic, such as the incorporation of a chromium oxide filter for accuracy, wavelength accuracy calibration, and built-in leak detections. So this is a summary and conclusion. We provide overview, the definition of UV detector and the listing of different detectors, focusing on UV vis and direct detector, glossary, fundamental, operating principle, flow cell, modern trend, I mentioned the standard detector for farm analysis is really a UV detector, or more specifically, a photodiode detector. On that note, we completed episode 16 on UV detector. Once again, we welcomed LCGC as a channel collaborator, and please subscribe for future video by subscribing to the YouTube channel. On that note, have a good day.